At 0642 on a gray winter morning, the control room lights flickered once, then steadied. Outside, the city was still asleep. Inside, machines worth billions waited for a signal that hadn't arrived yet. Engineers stared at dashboards glowing red with warning metrics. Output was falling, again. Not because the technology was broken, not because of sabotage, because of something far smaller. A delay so short it barely registered. Milliseconds stacking into seconds, seconds into minutes, minutes into losses no report could explain. Somewhere far away, systems were already failing because this room was late. Phones rang, unanswered. A supervisor whispered that if the numbers didn't recover by noon, contracts would be frozen, careers would end quietly, and no one could point to a single switch, a single mistake, a single villain. In the corner, someone who wasn't supposed to matter noticed a pattern no one else was watching. A motion repeated, a pause everyone accepted as normal, a flaw hidden so deep inside the process that it had become invisible. They didn't know it yet, but the next few minutes would decide whether this place stayed operational or became another silent example of how modern systems don't collapse from explosions, they collapse from tiny things everyone learns to ignore. At 0642, on a gray winter morning, the control room lights flickered once, then held steady. Outside, the city slept under a low blanket of fog. Inside, rows of monitors glowed with charts that refused to behave. Lines dipped where they should have risen. Numbers lagged behind projections that had been promised, signed, and sold months ago. No alarms screamed, no systems crashed, and yet everyone in the room felt it. Something was wrong. This facility was designed to run continuously. No pauses, no gaps, just smooth, uninterrupted flow. That was the promise. That was the contract. What it produced didn't matter to most people beyond these walls. What mattered was speed, scale, reliability. Entire downstream systems depended on it working exactly as planned. When it slowed, even slightly, the effects traveled far beyond this building. Engineers refreshed dashboards, supervisors checked timestamps, a manager rubbed his eyes and muttered that the night shift had reported the same issue. Output was down again, not dramatically, not enough to justify panic, but enough to trigger a familiar unease, the kind that comes when a problem refuses to show its face. At 0655, the first call came in, a partner facility asking why their scheduled intake hadn't arrived. At 0703, another message followed, this one more urgent. At 0711, a senior supervisor leaned over a console and whispered something no one wanted to hear. If the numbers didn't recover by mid-morning, escalation protocols would begin. Reports would be written, reviews scheduled, and once that happened, this place would never be quite safe again. The strange part was that everything appeared functional. Machines ran, conveyors moved, indicators stayed green. Each individual step passed inspection, and yet when the totals were added up, the math didn't work. It never quite worked. Somewhere between start and finish, time was leaking out of the system. By 0720, the floor below was fully active. The air carried a low mechanical hum, punctuated by the sharp clicks and whirs of synchronized motion. Workers moved through routines refined by months of repetition. Hands reached, objects transferred, processes completed. It all looked efficient, too efficient to question. That was the danger. When systems run the same way long enough, inefficiency stops looking like failure. It starts looking like tradition. In the corner of the control room, far from the senior engineers and their screens, someone stood without speaking. They weren't responsible for targets or contracts. They didn't sign reports or attend planning meetings. Their job existed one layer below decision-making, close enough to the process to feel its rhythm, far enough to notice its stumbles.
They watched the same sequence repeat again and again, not the machines, but the space between them, the pauses everyone ignored, the moments no graph flagged because they were too small to matter on their own, too brief to trigger alerts, too familiar to question. At 0728, a supervisor announced that adjustments would be made. Speeds nudged up, brakes shortened, focus sharpened, the usual response. Push harder, expect more, hope the numbers followed. They didn't. By 0741, the gap had widened, not enough to shut anything down, just enough to confirm a truth no one wanted to say out loud. This wasn't a one-off glitch, it was structural, something baked into the way this place worked, and that meant fixing it wouldn't be easy. Below, on the floor, the motion continued. Reach, transfer, reset, reach again. Smooth, predictable, almost elegant. Except for one thing. The pattern looped back on itself, a cycle pretending to be a straight line. The person in the corner felt it before they could explain it, a tension between movement and outcome, effort without proportional return. The system wasn't failing because it was weak, it was failing because it was designed to waste time so small no one had ever tried to save it. Yet. At 0752, another call came in. This one carried an edge. Delays were now officially logged. A countdown had begun, though no one used that word. The facility hadn't reached crisis, not yet, but it was drifting toward it in silence. And somewhere between the glow of the monitors and the rhythm of the floor below, an uncomfortable possibility was taking shape. What if the problem wasn't speed? What if it was motion?
At 8:05, the hum of the facility felt different. Not louder, not faster, just noticeable. The same machines, the same conveyors, the same workers moving in perfect repetition. But something had shifted. Someone watching closely could see it. Tiny hesitations, a micro-pause between every handoff, barely perceptible, yet in a place that ran by the second, those milliseconds stacked, multiplied, and vanished into the ether of lost output. The person in the corner, Alex, a technician who rarely spoke above a whisper, leaned closer to the railing overlooking the main floor. Alex had no authority here, just curiosity, and the rare combination of focus and patience needed to notice what everyone else had stopped seeing. Hands moved in circular motions, objects transferred from left to right, right to left, each movement smooth yet incomplete. Something about the rhythm gnawed at Alex. It wasn't random, it wasn't chaotic, it was predictable. And predictability, when harnessed, could be power. Alex scribbled on a small notepad, lines and arrows, circles and loops. It looked like doodles at first glance, but inside the spirals there was logic, efficiency hidden inside repetition, time wasted inside motion. Every pause, every shift, every lost microsecond could be recovered if only the system worked with the rhythm rather than against it. By 8:17, a supervisor walked past, muttering about quotas and delays. Everyone nodded, agreed, nodded again, then returned to their stations. Push harder, keep moving, don't stop. Numbers didn't lie, and the numbers were always a fraction short. No one ever asked why. No one ever looked beyond the charts, except Alex. Alex's eyes followed a tray sliding down the conveyor. The tray moved from station to station, hand to hand, moment to moment. At each stop, a worker reached, lifted, placed, reset. Then a pause, then the next transfer, step after step after step, over and over. By noon, Alex could almost predict the precise microsecond each motion would finish before the worker even began it, not because of skill, but because the system had trained the workers into a mechanical rhythm, a rhythm Alex had started mapping in circles. By 8:33, the pattern became undeniable, a circle hidden inside the line, a loop pretending to be linear.
human hands repeating motions that a clever machine could replicate and amplify without pause, without fatigue, without error. The realization hit Alex like a hammer. The solution wasn't pushing harder, it wasn't adding more workers, it wasn't tweaking speeds, it was rotation, continuous, repeating, synchronized, like a wheel, like something designed to carry motion instead of resisting it. Alex tapped the notepad, tracing the circles over and over. A concept began forming, a feeder wheel, multiple slots, continuous motion, every handoff baked into a rotation, not linear, circular, efficient, endless, each spin delivering output at the exact moment the next station expected it. No pause, no human fatigue, no missed microseconds. In theory, a single mechanism could do what dozens of hands struggled to accomplish across shifts. By 8:48, Alex's hand ached from drawing and redrawing designs, erasing and starting again. Notes were scattered across the desk, numbers, angles, sketches, ratios. If one rotation delivered 30 units and the wheel spun 9 times a minute, and if 3 wheels synchronized, output could double, perhaps triple, and all without increasing labor, without breaking the rhythm of the human operators. Alex's heart raced at the possibilities. At 9:02, Alex whispered to no one in particular, "It's not about force, it's about flow." The phrase lingered in the control room, unheard, but it anchored something critical in Alex's mind. Breakthrough isn't born from effort, it is born from understanding the system's hidden logic, from noticing what no one else sees, from imagining motion where everyone else assumes limitation. By 9:14, a small prototype idea had emerged, not built yet, not tested, not approved, just conceived in pencil and calculation, but it was solid and fragile and impossible. A wheel, a circular feeder, a rotation taking over the work humans had been forced to endure, microsecond by microsecond, for months. The blueprint wasn't in CAD software or official engineering diagrams, it was in Alex's mind, and soon it would have to leave the mind and face the floor. At 9:28, a minor jam occurred on the floor, the usual chaos. Supervisors swore under their breath, workers reset trays, minutes lost. Alex froze, watching. The problem wasn't the jam itself. The jam was a symptom, a mechanical truth revealed. The linear process couldn't sustain continuous efficiency. Pause after pause, delay after delay, time bled. The system was a sieve, letting seconds slip away. Every lost second multiplied across the plant, across the day, across contracts and deadlines. By 9:41, the notion became undeniable. If Alex's wheel concept worked, even partially, the plant could reclaim lost time. Margins could be recovered. Microseconds could become hours. Effort could turn into impact. And most importantly, the invisible bottleneck, buried in repetition, disguised as routine, could finally be challenged. The question wasn't if the wheel could exist. The question was whether anyone would let it happen. And Alex knew one thing. The next few hours would decide whether observation became action or remained a whispered insight lost in the hum of machines.
By 10:05, the factory floor had fallen into its relentless rhythm. Conveyor belts clattered, metal clanged. Workers moved with practiced precision, their arms swinging in synchronized loops. Alex stood by the edge of the line, notepad in hand, heart hammering. The concept was clear. The wheel, circular motion, continuous feed. But the reality of building it, that was a different problem entirely. Using scavenged parts from a maintenance corner, Alex began assembling a crude mock-up. A wooden ring from a discarded crate, small slats nailed unevenly around its perimeter, a makeshift spindle balanced precariously on 2 blocks. It was ugly, it was fragile, it was a joke to anyone looking in. But it was also the first step. The first few minutes were chaos. The wheel wobbled, a casing fell short, bounced off the concrete, clattered into a bin. The second spun too fast. The third didn't spin at all. Sweat ran down Alex's temple as workers paused to glance, curious, skeptical, amused. Supervisors muttered under their breath, shaking their heads at the audacity of trying anything new. Yet Alex persisted, adjusting angles, tightening slats, rebalancing the spindle, one tiny improvement at a time. Each rotation revealed flaws, each flaw taught a lesson. By 1028, something remarkable began to happen. One casing stayed on track, then two, then three. Not perfectly, not consistently, but a pattern emerged. Motion could be controlled, rotation could be harnessed, flow could be learned. A worker from Line 4, a veteran who had moved casings for more than 10 years, approached. "What are you even trying to do?" he asked, curiosity masking skepticism. Alex explained with trembling hands the concept of rotation, continuous feed, reduction of wasted time. The veteran studied the wheel, tapped it lightly with a calloused finger, and nodded slowly. "Could work, if it doesn't fall apart." The next hour became a dance between imagination and reality. Casing after casing, spin after spin, small victories stacking up amid failures. Each jam taught a micro-lesson. The angle needed slight adjustment, the weight needed redistribution, the rotation needed calibration. Alex documented everything meticulously, every error, every successful feed, every wobble. By 11:45, something clicked. The wheel rotated steadily, delivering casings with an uncanny rhythm. Not flawless, not yet perfect, but a recognizable motion. One line station had a small taste of what could be. Workers began noticing, eyes widened, hands paused, whispered comments circulated. "Is that actually working?" But then reality intervened. At 11:52, the spindle slipped, sending the wheel into a violent wobble. Casings flew in every direction. A minor jam froze the line for several minutes. Alex froze with it, heart sinking. Laughter erupted from some corners, frustration from others. This was failure, raw and public. The prototype wasn't ready. Yet something subtle had shifted. Supervisors didn't immediately scold. Engineers didn't dismiss. They watched. Why? Because for the first time, a tangible proof existed. The problem was visible. The solution had begun to materialize, even if imperfectly. The old rhythm of defeat, push harder, longer, faster, had been challenged. Alex stood back, chest heaving, hands trembling, eyes scanning the chaos. Notes in hand, mind racing. Failure had a lesson embedded. Speed without stability was meaningless. Rotation without alignment was useless. But the potential was undeniable. By 12:03, Alex began recalibrating. Rubber gaskets from discarded tires were added to reduce vibration, weights redistributed to stabilize the ring, slats realigned to ensure casings wouldn't slip. Every small tweak brought the wheel closer to precision. Every adjustment made it clear. The first attempt didn't fail, it instructed. At 12:25, the wheels spun again. Casings fell into the alignment channel more consistently, slightly faster, slightly smoother. The rhythm was improving. Alex's eyes met the technician from Part 2, mutual understanding passing between them. Progress, however fragile, was underway. By 12:40, Alex paused, surveying the line. Workers glanced, supervisors scribbled notes, engineers whispered among themselves. Everyone recognized it without saying it. Something different had been born. Not perfect, not final, but alive. Motion controlled, potential unleashed. Alex's voice, barely above a whisper, repeated the mantra that had kept focus through failures. Flow, not force. Rhythm, not repetition. Continuous, not broken. The stage was set. The first prototype had lived. The next step would be building a real industrial version, strong enough to survive the factory's chaos. And when that moment came, the plant and the war might never look at efficiency the same way again.
By 1400, the factory had settled back into its relentless rhythm, but Alex's mind refused to settle. The wooden wheel had proven the concept. Now came the real challenge.
industrial strength. The kind of machine that could endure hours of relentless motion, vibration, heat, and human error without faltering. Every second lost on the line meant thousands of rounds missed, and the war didn't wait for mistakes. In the maintenance bay, scraps of steel glinted under harsh white lights. The night crew had been instructed to prepare heavy-duty materials: steel plates, a thick spindle, rubber linings salvaged from old vehicles, and industrial-grade bolts. Nothing delicate, everything robust. Alex studied the pile like a sculptor choosing raw stone. Every piece had to survive the unforgiving demands of production. By 1415, assembly began. Mechanics and engineers surrounded the design, eyes tracing Alex's rough sketches. The central ring was larger, precisely measured, each recess carved to cradle ammunition casings securely. Rubber linings absorbed vibration, ensuring each spin remained smooth. 3 wheels were planned, staggered to maintain continuous feed. Alex explained the principle again: staggered rotation, continuous alignment, reduced human strain. The engineers nodded slowly, some skeptically, some intrigued. By 1500, the first steel wheel was mounted. It was heavy, overbuilt, imposing, a far cry from the fragile wooden mock-up. The spindle bore the weight with slight flex, just enough to absorb shocks without breaking. Mechanics tightened bolts, adjusted angles, rechecked alignment. Every millimeter mattered. One misaligned slot could jam the line and cost thousands of rounds. Alex stepped back, heart racing. "Let's see if this survives 5 minutes," whispered one engineer. Power was applied. The motor hummed. The wheel groaned under its own weight, then spun, slowly, deliberately, steadily. Casings were loaded into the first recesses. The wheel carried them forward. One fell perfectly, the next followed, and the third wobbled, then corrected itself. A murmur rippled through the group. By 1523, they had increased the speed slightly. The staggered wheels began moving in unison. Casings flowed from one wheel to the next, a chain of mechanical precision that hadn't existed in the plant before. Workers watched from the line, hesitant, hands paused mid-motion. The rhythm of the factory began to feel different, less frantic, more controlled. By 1540, the first true test was underway, a full minute under real conditions. The wheel rotated continuously, casings aligned accurately, minimal jams. Productivity estimates skyrocketed in Alex's mind. The numbers weren't just theoretical anymore, they were tangible. Every 1% improvement in throughput translated into millions of rounds per month, and that meant lives saved on distant battlefields. But perfection remained elusive. At 1552, the second wheel wobbled under uneven weight. A casing bounced off the chute. Alex's heart skipped. The engineer adjusted tension rods. Mechanics added stabilizers. By 1605, balance was restored. The lesson was clear. Industrial machines demanded iterative refinement just as much as human observation had guided the first wooden prototype. By 1625, all 3 wheels operated in unison. Casings fed smoothly, continuously, almost hypnotically. The flow had been tamed. Human fatigue was reduced. Stops and starts were minimized. The plant felt alive in a new way, a mechanical heartbeat synchronized with human hands. At 1640, Alex stepped back, wiping sweat and grime from their brow. The prototype wasn't just working, it was transforming the line. Supervisors, who had been skeptical all morning, exchanged glances. Engineers scribbled notes furiously. Even the night crew, hardened by years of tedious labor, whispered in awe. By 1700, the prototype had proven itself for 20 uninterrupted minutes. Throughput estimates indicated a near doubling of production. Bottlenecks had been reduced to near elimination. Each rotation delivered casings with predictable accuracy. Workers adjusted naturally to the rhythm, hands moving in tandem with the wheels instead of fighting against them. Alex allowed themselves a quiet smile. This was the first step towards real change, not just for one line, not just for one plant, but potentially for every plant feeding ammunition to the front. The war depended on numbers, and numbers were now within reach. Before the evening shift began, Alex documented every detail: angles, RPMs, weight distribution, rubber thickness, staggered wheel timing. Every variable mattered. The next day, scaling the design to the remaining lines would begin, and if it succeeded, Lake City would push beyond its previous limits, surpassing quotas, saving lives, and setting a new standard for wartime innovation. At 1745, the prototype was disassembled carefully for inspection. Mechanics and engineers noted minor adjustments: deeper recesses for stability, slight redistribution of weight, reinforcement of spindle mounts. Alex made mental notes. Each improvement would compound, turning a simple sketch into a machine that would redefine efficiency. And as the sun dipped behind the factory's smokestacks, Alex realized something profound. The smallest observation, a pattern in human motion, had blossomed into a tangible industrial solution. The wheel wasn't just a machine, it was a catalyst, a signal that even in the most chaotic, rigid, unforgiving environment, innovation could thrive. The stage was set for Part 5, where the wheels would be installed on live production lines, tested under the full weight of wartime demands, and the true impact of Alex's idea would begin to ripple through the plant and beyond. At 6:30 the next morning, the Lake City plant stirred under a humid Missouri sky. Steam rose from furnaces, presses rattled brass into casings, and conveyor belts vibrated under the weight of thousands of rounds. The day crew arrived, unaware that something unprecedented was about to unfold on Line 2. Alex stood beside the freshly assembled steel wheels, now mounted on the production line. The prototype had been reinforced overnight, every recess calibrated, every spindle tightened. The staggered three-wheel system glinted under the fluorescent lights, heavy and precise. Workers paused, exchanging puzzled glances. Nothing like this had ever been on the floor before. By 6:45, the foreman gathered the crew. His tone was clipped, but carried an unusual edge of curiosity. "We start slow. Watch the rhythm. Don't interfere. If it fails, we shut it down. If it works, you'll feel it before you see it." Hands moved cautiously. Casings were loaded into the first wheel. Alex stepped back, heart pounding. The motor was switched on. The wheels turned. At first slow, careful, testing the tolerances under the weight of actual production. Casings dropped into the alignment channels one by one, some hesitating, some wobbling, but none falling catastrophically. By 0703, the system found its rhythm. The staggered rotation began feeding continuously. Workers' hands synchronized with the motion instead of fighting it. Stop and start jams that had plagued the line for months vanished. Supervisors scribbled numbers frantically, noting every second gained. Alex could barely breathe, eyes fixed on the counter. At 0720, the first 10 minutes of full-speed operation were complete. The line had already surpassed its usual output for that time. Casings per minute ticked higher than anyone expected. The foreman's jaw tightened. He whispered to an engineer, "Is this real?" The engineer's eyes were wide, not with disbelief, but cautious hope. By 0720, minor flaws appeared, small wobbles, one casing misaligned, but the wheels corrected themselves within rotations. Each minor error became an opportunity for observation, not panic. Workers began to relax, their movements fluid, confident. Fatigue, which had always been a hidden enemy, was diminished. The machine carried the weight that had worn down human wrists for years. At 0730, Alex allowed themselves a glance at the counters. Output was rising steadily. Line 2 had historically stalled at 23,000 casings per hour. Now the numbers projected 50,000 or more if this pace continued. Each incremental gain represented thousands of rounds, thousands of lives in distant battlefields. By 0738, engineers measured rotations, tested alignment, and noted stress points. The staggered three-wheel design was performing almost flawlessly. The line seemed alive, a mechanical heartbeat pulsing through brass and steel. Supervisors whispered among themselves, calculating monthly production projections. If this scaled to all lines, quotas that had seemed impossible were now within reach. By 0750, Alex observed the human element. Workers' eyes, once glazed with fatigue, now followed the movement with attention and understanding. Their hands no longer strained against the conveyor rhythm, they flowed with it. The factory itself seemed to exhale, a coiled tension finally released. By 0805, a full 35 minutes into live operation, the wheels began to demonstrate consistent performance under full load. Minor jams were corrected in seconds, efficiency gains compounded. Alex could feel it, the difference between concept and reality, sketch and steel, idea and revolution. At 0815, the foreman finally spoke to the assembly floor. "Keep watching, keep feeding. This could change everything." There was no cheer, no fanfare. This was a war plant. Victory came in numbers, not applause. But the quiet awe in the room was palpable. By 0830, Line 2 had recorded a full hour's worth of output exceeding the plant's previous daily peak projections. Engineers whispered about scaling to Lines 3 and 4. Alex's design was no longer theoretical, it was a functional, scalable solution. By 0845, Alex allowed themselves a slow breath. The prototype wheel had survived its first test, but beyond survival, it had proven something more profound. Even in a rigid, high-pressure wartime system, observation, courage, and iteration could overcome entrenched limitations. The smallest insight, a circular motion, a pattern in human hands, had blossomed into a tangible breakthrough. Before lunch, adjustments were made. Rubber linings were reinforced, spindle mounts slightly strengthened, and wheel angles fine-tuned. Each change was minor, but each would ripple through every future rotation, compounding into massive efficiency gains. Alex scribbled notes feverishly, already envisioning the full-scale implementation. By 12 o'clock, the factory hummed as usual, but Line 2 was different. It moved with precision, confidence, and power. The prototype was no longer an experiment, it was a statement. Efficiency could be redesigned, productivity could be multiplied, and even a 19-year-old's observation could challenge decades of industrial tradition. And somewhere beyond Missouri, across oceans and battlefields, those thousands of rounds being produced at a pace once thought impossible were now on a path to impact the war in ways Alex was only beginning to imagine. By 5:30 the next morning, Lake City had become a different place. The hum of machinery felt charged, anticipating what the new day would bring. Line 2's prototype had survived its first live test, but the challenge now was larger. Could the system scale across the entire plant without halting production? Alex arrived before most workers, clutching a notebook filled with revised calculations. The staggered wheels, reinforced and adjusted, had proven their worth. But one line could not carry the entire plant. Lines 1, 3, and 4 were still shackled by linear feeders, by stop-start jams, by the silent enemy of lost seconds. Each line was a bottleneck, a choke point threatening the war effort. By 0600, the plant engineer had gathered a small task force. Line supervisors, mechanics, and procurement officers surrounded Alex as they examined the prototype. "We can't risk downtime," one supervisor said bluntly. "If we pause the other lines, even for calibration, production drops. Washington won't forgive it." Alex nodded, understanding the stakes. "We won't pause. We'll implement a phased installation. Wheels go live sequentially, each line tested individually, then synchronized." They pointed to sketches of 4-wheel arrays, each staggered system feeding the next, a mechanical heartbeat running through brass and steel. By 0700, preparations began. Mechanics and engineers moved swiftly, installing additional wheels on Line 3. Each rotation was measured, tension adjusted, alignment double-checked. Workers, skeptical at first, watched closely. Some muttered disbelief. A kid's sketch running the show? Yet even in doubt, their hands adapted. They fed the first casings into the wheels carefully, almost reverently. At 0725, Line 3 started its first rotation. Small wobbles appeared, but the wheels self-corrected. Casings fell cleanly into alignment channels. Output climbed almost instantly. Supervisors scribbled numbers frantically. Productivity gains mirrored Line 2's success. By 0800, Line 1 and 4 were prepped. Alex paced the floor, heart hammering. Every decision mattered. Every adjustment counted. If even one line failed, it could cascade into hours of lost production. At 0815, Line 1's first rotation began. The staggered wheels groaned under the weight of 50,000 casings per hour, but they held. Casings dropped seamlessly, rhythmically. Workers' hands moved with them. The repetitive strain eased. By 0830, Line 4 followed. The full array now stretched across the plant, a symphony of rotation, steel, and motion, feeding brass with a precision no human hands could match. The engineer ran the numbers quietly. If scaled to all shifts, the daily output could more than double. Washington's quota of 2.4 billion rounds per month, once impossible, now seemed attainable. Alex realized something profound. They hadn't just improved efficiency, they had reshaped the factory's logic, rewritten the invisible rules that dictated wartime production. By 0900, Alex stepped back to observe the synchronized lines. The staggered wheels rotated in perfect unison, a mechanical choreography. Workers adapted to the new rhythm, fatigue visibly reduced, errors nearly eliminated. The factory itself seemed to pulse with life, each wheel a beating heart pumping rounds into the war effort. By 0930, minor adjustments were made on the fly. Small wobbles, slight misalignments, corrected instantly. Alex noted each variable: rotation speed, weight distribution, rubber lining resilience. Each small correction compounded into enormous gains. Each minute saved now represented thousands of additional rounds reaching frontline soldiers. At 0100, the foreman addressed the assembly floor. "Watch your hands, watch the wheels, learn this rhythm. This is the new standard." Workers nodded, eyes wide, recognizing the magnitude of the shift. Efficiency had ceased being theoretical. It had become tangible, auditable, unstoppable. By 1200, a memo went to Washington. Experimental efficiency gains underway, projected output increase verified. Names were absent, as always in wartime bureaucracy, but numbers spoke louder than credit. Tens of thousands of rounds, multiplied by hours, multiplied by days, now moved through Lake City at a pace once thought impossible. By 1300, Alex allowed themselves a slow breath. The factory was alive with the pulse of innovation. Lines 2, 3, and 4 rotated in perfect harmony. Bottlenecks were gone, fatigue minimized, output soaring. The observation that had started as a fleeting insight in a 19-year-old's mind had now reshaped an entire industrial ecosystem. By 1400, supervisors began projecting the impact on combat units. Infantry in Sicily, Marines in the Solomons, fighter squadrons over Europe, they would receive ammunition faster than ever before. Small gains at Lake City would ripple across oceans and battlefields, saving lives, preserving operations, determining outcomes. Alex realized something extraordinary. Innovation in wartime didn't require grand titles, degrees, or authority. It required vision, observation, courage, and relentless iteration. And in this factory, on this humid July day, the tiniest insight had become the machinery of victory. Before moving on, Alex paused to reflect. Could this principle, observation, iteration, courage, be applied beyond Lake City, beyond ammunition, beyond war itself? The answer whispered in the hum of the steel wheels. Yes, it always could. By 0445 the following morning, Lake City was already alive with anticipation. News of the synchronized staggered wheels had spread through whispers, cautious nods, and incredulous glances. Everyone, workers, supervisors, mechanics, knew something unprecedented was unfolding, yet no one fully grasped how critical the next 24 hours would be. Alex arrived early, carrying revised sketches, stopwatch in hand. Each minute now mattered more than ever. Across the plant, the newly installed wheels had been running all night, feeding casings without pause. But continuous testing was essential. Materials fatigue, heat expansion, subtle misalignments, any failure could cascade into massive downtime. Washington expected results, and the front line waited. By 035, Line 2 pulsed like a living organism. Wheels rotated, casings slid, alignment channels channeled the brass seamlessly. Line 3 followed. By 06, the entire plant was synchronized, each line operating at peak capacity. Workers had adapted to the rhythm, moving in tandem with the rotating carriers. Fatigue seemed diminished, strain reduced. But the real test was endurance. Could the system maintain peak output under relentless hours? Alex ran the first audit. Stopwatch in hand, they recorded output, revolutions per minute, and minor deviations. The numbers were staggering. A single station now exceeded previous expectations by 60%. Across 4 lines, daily throughput could potentially double. Tens of thousands of rounds now moved through the plant every hour, rounds that would reach the Solomons, Sicily, and the skies over Europe. By 0715, the first hiccup appeared. A slight wobble in Line 4's secondary wheel threatened to misalign casings. Alex signaled the mechanics. Within moments, the spindle was adjusted, tension retuned, and alignment corrected. What could have been a catastrophic stoppage became a minor blip. The team had learned to respond faster than the machine could falter. By 8 a.m., foremen walked the floor in awe. The factory had shifted from a place of labor to a place of precision choreography. Observers from Washington would later describe it as organized chaos but with rhythm. Every wheel, every belt, every human hand now functioned as part of a larger, harmonious system. By 9:30, Alex noticed a subtle pattern. Small improvements, minute adjustments to wheel angle, the timing of feed, rubber lining resilience, compounded hourly. Efficiency gains were exponential. What had started as a 5% improvement now projected toward 15% across the plant. That meant millions more rounds per day, potentially tipping entire campaigns. By 10:45, the stakes escalated. Word arrived via telegraph. A critical convoy transporting ammunition to North Africa had been delayed. Combat units were running low. Every minute saved in production could directly prevent a disaster on the front line. The pressure intensified. The wheels must not falter. At 11 a.m., Alex walked past the lines, observing every worker, every rotation, every minor variation. They realized the factory was no longer just a building, it was a weapon, operating silently, invisibly, but with consequences that could decide battles. One misalignment, one jam, could ripple across oceans into the hands of soldiers. By 12:30, engineers suggested further automation tweaks, small mechanical linkages to reduce manual intervention, but Alex hesitated. The human element, the observation, the feedback loops from the workers themselves were as critical as steel and rubber. Removing it risked losing the adaptability that had saved the prototype countless times. By 13:15, Line 1 achieved a milestone, 80,000 casings per hour without a single stoppage. Alex ran the tally. Across the plant, the theoretical output for the day surpassed what had previously been achieved in an entire week. Every second saved multiplied into thousands of rounds, thousands of potential lives, thousands of bullets reaching soldiers who needed them most. By 1400, morale shifted. Workers who had been exhausted, strained, and skeptical now moved with purpose, with belief. The factory had become more than machines. It had become a testament to human observation, persistence, and ingenuity. By 1545, Alex and the engineers observed a pattern emerging. Minor deviations now self-corrected naturally due to the synchronized rotations. What was once chaos became self-stabilizing. The system now anticipated failure points and compensated, a mechanical foresight born from careful iteration and countless tests. By 1630, Washington received the first real data. Output was exceeding quotas by nearly 20%. The report was cautiously optimistic, but behind every number lay the unseen orchestration of wheels, humans, and intuition. One teenager's insight had reshaped the flow of war material across the globe. By 1700, a challenge emerged. A batch of defective casings threatened to jam the feeder system. Alex, observing the sequence, realized that minor adjustments to alignment lips and feed angles could compensate. Mechanics implemented the change instantly. The batch moved through without incident. Victory here wasn't dramatic. It was silent, incremental, and powerful. By 1800, the plant settled into a steady rhythm, the pulse of wheels a constant, reliable heartbeat. Workers paused only briefly, catching their breath, exchanging glances that conveyed unspoken pride. They understood the scale of what was happening, even if the world outside would never know their names. By 1900, Alex allowed himself a moment of reflection. The principle was clear. Innovation didn't arrive in flashes of genius. It was iterative, it was persistent. It demanded observation, courage, and the willingness to adjust minute by minute. Every tiny improvement compounded into a machine that could tilt the course of the war itself. As dusk approached, the hum of the factory shifted from frantic intensity to confident momentum. Lake City had become more than a plant. It had become a machine of possibility, a network of coordinated movement, a silent force underpinning victories yet to come. Before the final chapter, Alex pondered a single truth. The real victories of war often occurred far from the battlefield, in the hum of machines, in the precision of motion, in the courage to test, fail, and adjust. The outcome of entire campaigns could be rewritten, and Lake City was proof.
By 5:30 the next morning, Lake City Ordnance Plant seemed unchanged. The same heat pressed against steel beams, belts rattled, furnaces hissed, and workers shuffled in with bleary eyes. Yet something had shifted, intangible but undeniable. The factory now breathed differently, its heartbeat steadier, its pulse more confident. Alex stood beside the rotating feeder on line 2, eyes tracing the motion of casings gliding effortlessly into alignment channels. Every wheel spun in perfect synchronization, the feed continuous, the human effort harmonized with the machine. For the first time, output wasn't a struggle. It was a rhythm, a controlled, predictable force. By 6:15, the morning audit began. Supervisors recorded numbers, engineers calculated throughput, and Alex, watching quietly, felt a weight lift from their chest. One station that had previously struggled with 23,000 casings per hour now exceeded 75,000. Across the plant, projected daily output had nearly doubled. Millions of rounds were now being produced that day alone, enough to sustain multiple operations simultaneously, enough to tip entire campaigns. By 7 o'clock, Washington's observers arrived, skeptical but curious. They watched the system in motion, eyes narrowing as casings flowed smoothly, hands moved with less strain, and jams became virtually non-existent. They questioned, calculated, and finally they nodded. The numbers were undeniable. Lake City was no longer constrained by human repetition or linear motion. It had become a machine capable of sustaining the war effort on an unprecedented scale. By 8 o'clock, a report was drafted and sent to field commanders. It was concise, factual, and stripped of names. But the implications were massive. Ammunition shortages could now be alleviated, training could proceed without rationing, and frontline units could engage without fearing empty belts. The war, in countless small ways, had shifted. By 9:15, the factory hum was joined by whispers of pride. Workers exchanged glances, subtle smiles, and nods. They had become more than laborers. They were the hidden force behind every round leaving the plant. They understood that every motion saved seconds, and every second multiplied across lines, shifts, and days could determine whether a soldier survived, whether a hill was taken, whether a mission succeeded. By 10:30, Alex walked the aisles, notebook in hand.
Adjustments had been made overnight, angle refinements, deeper recesses, reinforced spindle mounts. Each iteration improved efficiency. The factory had become self-teaching in a sense. Each failure corrected itself through observation, feedback, and incremental change. Innovation wasn't a flash of brilliance, it was persistence, refinement, and courage to act on insight. By 12 o'clock, the first full-scale batch of 1.4 million rounds moved through the plant without a single jam. Engineers recorded every detail: motor speed, feed timing, wheel rotation, vibration absorption. The data confirmed what Alex already knew. The wheel worked not because of its design alone, but because human observation had guided it, adjusted it, and nurtured it from a crude wooden mock-up to a steel instrument of efficiency. By 14 o'clock, news of Lake City's breakthrough began trickling to military strategists overseas. Commanders in North Africa and Europe noticed improved ammunition flow, fewer supply shortages, and increased readiness for upcoming offensives. A small innovation in Missouri had extended its influence thousands of miles away, shaping battles without a single shot fired by those who invented it. By 16 o'clock, Alex allowed themselves a quiet moment. Standing beside the rotating wheels, they reflected on the journey. The idea had started as a fleeting observation, a memory of an old Gatling gun mechanism, an impulse to rethink repetitive motion. That single insight, nurtured with patience, courage, and relentless iteration, had become a tool that could influence the outcome of the war. By 18 o'clock, the factory's momentum was undeniable. Wheels rotated, belts carried brass with metronomic precision, and humans moved in harmony with machines. Every lost second from the past had been reclaimed, every bottleneck had been dismantled, and across the world, soldiers unknowingly benefited from the unseen heroism of observation and ingenuity. By 1930, Alex addressed the team quietly, words simple but profound. This isn't just steel or wood, it's effort, observation, and courage. It's not the fastest hands, the strongest arms, or the biggest machines that win wars. It's understanding the system, seeing what others overlook, and daring to act. As dusk fell, the wheels continued to spin. The factory, once constrained by human limits, now operated as a cohesive force. The war outside would rage on, but Lake City's hidden revolution had already begun shaping its course. Millions of rounds would reach the front lines, soldiers would fight with a renewed edge, and lives would be saved, all because one person saw a loop in motion and dared to transform it into momentum. By 20 o'clock, the plant exhaled, not in fatigue, but in steady confidence. The lesson was clear. Even in war, innovation could come from unexpected places, and the quiet, persistent pursuit of improvement could ripple across oceans and battlefields. And somewhere, in every bunker, trench, and landing craft, a soldier's hands gripped a rifle loaded with brass that had traveled through that rhythm, that heartbeat, that wheel. And history quietly changed, not by a single act of heroism, but by the power of observation and the courage to act.